All right, here we go. We are going to today learn about how to make graphs that describes constant velocity. And so, once again, objectives are here. Read them. Off we go. All right. So I put together this little number line here, right? So let's assume I realized I didn't put units on it. So we're going to, assume that all of these positions are in miles, okay? So the position of Roy's house is 0 miles, the position of Bob's Triangle store is 12 miles, etc. All right? So in the example here, it says, suppose Roy begins at home and walks to the right at 3 miles per hour. So let's think about what's going to happen. So what that means is he's going to be right here when we start our clock, right? So we're standing there, we're with a clock, right? Stopwatch. Roy leaves his house. We're like, ready, set, go. And we click start right when Roy begins walking. So t equals 0 represents the moment at which Roy begins walking. Okay. And he's going to go 3 miles per hour. So after 1 hour, he's going to be here at White Castle. In the next hour, he's going to go another 3 miles. So he'll be here at 6. All these times are in hours. Another hour later, he'll be over here. Another hour later, he'll be at the Triangle store. T equals 5. T equals 6. So what's he doing? He's going 3 miles every hour, right? Okay. So this little map here is handy because I can sort of use it to mark his location at different times, but it gets a little bit cumbersome. And plus, I've only recorded his position at very specific instants, right? Like, where is he after 3.75 hours? I don't know, right? So let's see if we can sort of put this into a more useful presentation. All right. So what I've got here is what's called a position time graph. Okay, that is important. We're going to be using these all year. This is called a position. It's so important that I'm going to write it in really small letters in the corner of the board. It's a position time graph. Okay, because it tells us the object position at a given time. All right. So what I'm going to do is I'm going to think of each of the points that I had up here as a coordinate point. So my x-coordinate, my horizontal coordinate, is the time. My vertical coordinate is the position. Now this is a little bit confusing because our symbol for position is x, and x actually goes on our y-axis. And then our x-axis is time, okay? So it's position, time. All right, and so let's go through and plot those points. So what we discovered was that at time 0, Roy was at home, right? And then he goes 3 miles every hour, right? So after 1 hour, he's going to be here at a position of 3. After 2 hours, he'll be at a position of 6. Plus 3 gets us 9. Plus 3 is 12. Plus 3 is 15. Plus 3 is 18. Oh, cool. It looks to me like this is a straight line, isn't it? Let's make our line red. So here we go. Oh, look at that. It's a nice straight line. So there we go. Position time graph. All right, so let's do this. So it's a line. So in math class, one of the things we learned how to do is to find the slope of a line, right? Or to find the equation of a line, right? Y equals mx plus b, right? So let's come up with the equation of this line. So in order to do this, I need to find the slope, right? So let's see. So slope is just rise over run. So let's pick 2 points, whatever. I'm going to pick 2 arbitrary points. How about this point and this point? Okay. And so if I do that, then my rise is, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So my rise is 12 meters, right? Or 12 miles, rather, right? So rise over run. My run is 1, 2, 3, 4 hours, right? So my slope is rise over run. So let's see, I went up a position of 12 miles in 4 hours. Oh, well, that's 3 miles per hour, isn't it? That's my velocity. Ooh, that feels like an important thing that I should write down. We just discovered a thing. The slope of a position time graph gives technically average velocity. It's the average velocity between the 2 points. Okay, but here, since my line was straight, a straight line on a position time graph, straight line on a position time graph means constant velocity. And when I mean straight, I simply mean not curved. In other words, this red line here is, in fact, a straight line, right? Okay, so, cool. So that feels important. We just found out a thing. All right, so we've dealt with the slope. Let's see if we can figure out what's going on. So we know our slope is, here, let me do this. So we know that the slope is our velocity, right? Well, let's see if we can figure out what's going on over here with b, all right? So let's see. We already did that, we did that, all right. So I think in order to do that, what I'm going to do is let's go backwards and use the graph to find the velocity. And this is actually what we just did, right? Maybe I shouldn't have done this. So I'll tell you what, why don't you do this? So you've got this graph here. See if you can find the velocity of this object here. Okay, so basically what you should be doing is finding the slope, right? So pause the video, find the slope. I'm going to assume you just did that. I'm going to do it really quickly. So here's my slope, rise over run. So I'm going to just pick 2 points. So burp, burp. So it looks like every hour, oh wait, what are my units here? Every second we go 4 meters, right? So my slope, and therefore my velocity, is 4 meters per second, right? Because every second I go 4 meters. Every second, 4 meters. Every second, 4 meters. Every second, 4 meters. Every second, 4 meters, right? Okay, cool. So that's that. All right, so now this blue line that's here on this graph is the exact same as the one that was on the last graph, right? But I've added in this red line. How is the red graph different? Well, the lines are parallel, so they have the same slope, right? So both of these lines have the same velocity. All right, well, how are they different? Well, the red graph starts higher up. It starts here at 6. Well, okay, so think about what these intercepts are telling us. They're telling us at time equals 0 what the position is. And so for the red graph, the starting position is 6 meters, and for the blue graph, the starting position is 0 meters. Oh, that's my initial position, right? And in the equation, y equals mx plus b, b is your y-intercept. So b is your starting position, right? b is your starting position. So let's write an equation for this red line. So red line, y equals mx plus b. So let's think about what this is. So y is my vertical axis. That's position. So this is a little bit confusing. Unfortunately, y is x. So here we go. X, this is x as in position, not x as in x-axis, equals m. Well, remember, we decided that the slope was velocity. All right. What's on my x-axis? Oh, that's time plus, we decided that the y-intercept was the initial position, right? Right? Oh, wait a minute. And this is actually telling me the position after some amount of time t. So this is x final. Look at this equation, you guys. If I subtract xi from both sides, watch what happens. Something really cool happens. So I'm going to subtract xi from both sides. X final minus xi equals vt. Oh, that's displacement. This is what we learned in the last video. Oh, so we learned 2 equations for displacement. We learned this one, and we learned this one. There's no significance to the color I'm using right now, by the way. So if you combine these 2 equations and set them equal to each other, it gives you the equation for the position time graph. Okay? So, how are these two graphs different? They have the same velocity, but different y-intercepts and therefore different starting positions. Okay? All right. How is this green graph different? Well, pause it and see if you can come up with an answer. All right. So I'm going to assume you've done that. So let's see. So let's compare the red and the green graph. If for whatever reason if you are maybe colorblind, the green graph has triangles, the red graph has squares. Okay, so they both have the same starting position, right? The only difference is the slope, right? And the green one is a smaller slope, right? The red one, we've already established that the slope of the red one, so the velocity of the red one was, what was it, 4 if I remember right? Why can't I count? Yeah, it's 4 meters per second. Well, the slope of the green one is, well, let's see, in 1 hour we go 2 meters. Oh, so the green one has a velocity of 2 meters per second. So this one has an equation of position is velocity times time plus initial position. Okay? So, all right, purple graph. Ooh, this one is different than all of the other graphs, right? Because it slopes downhill. So what does that mean? What does that mean? So let's think about this. So in all of these other examples, our position is increasing, right? Because our vertical axis, remember, the vertical axis is position. So the position's increasing. And in the purple one, the position's decreasing. So let's go back to our number line back here at the beginning and think about what's happening. Clear out my ink here. So in order for the position to increase, that means I've got to be moving this way. And in order for the position to decrease, it means I've got to be moving this way, right? Oh, decreasing position means my graph is going to slope downhill. Moving backwards means it's going to go downhill. Oops, wrong way. So this purple graph here, oops, too far. Purple graph, this guy is going backwards. Oh, and in fact, let's find the slope. The slope is rise over run. So in 1 hour, we go back 3 meters. My run is -3. So my velocity, remember the slope is the same as velocity. This is a negative slope, therefore a negative velocity of -3 meters per second, right? And then my starting position looks like it's 48 meters, right? So see if you can write the equation for that purple line. So the position at some time is going to be velocity times time plus your starting position, which is 48. My phone is ringing. Can I pause it? I can. All right. So that's that. All right. And then let's look. I think I've just got one more graph here and we're all done. This orange graph. What's going on there? The position is constant, right? Position's constant. It's always 25, right? Oh, so this is just the graph x equals 25, right? Meters, I guess, right? Okay. So that's that. Oh, all right. So I forgot. I do have one more slide here. All right. So if we're given a position time graph, what can we do? Well, you can determine if the position is constant. In other words, if the object is stopped. We just saw that, right? You'll get a horizontal line, right? Your graph, position, time, your graph will be a horizontal line, right? Showing constant position. All right. If the velocity is constant, what does that look like? Oops. What does that look like? Well, we haven't seen anything yet where the velocity is not constant. So it's tough to sort of come up with a contrast. We will get to these problems later where the velocity is not constant. But so for now, what you need to know, the velocity is constant anytime your graph has a straight line. So remember, by straight, I just mean not curved. Position, time. So this is a straight line. This is a straight line. This is a straight line. Okay? Clearly, you can determine the position at any time, right? Just look at the time and find the position. All right? You can determine the displacement between two times. All right, just by subtracting the two positions at those two times. And you can find the average velocity by finding the slope, which is, to be clear, the same as doing, oops, which is the same as doing right? Rise over run. Haha. Cool. Oh, and that, incidentally, remember in the last video I said sometimes there's a delta down there? That's why, right? Rise is how much your vertical axis changes. Run is how much your horizontal axis changes. It's the change between two different time coordinates, I guess. All right? All right, so we talked there about interpreting the graphs. You can also draw the graphs, all right? So here's a quick example. So what if I gave you this? What if I gave you a starting position of 5 meters and a velocity of 3 meters a second? You guys know how to do this, right? We just did this a whole bunch, right? Let's see, my starting position is 5. Velocity is constant at 3. So here's what I would do, honestly. So let's do this. Let's mark our starting position. It's at 5. Let's do this. Let's figure out what the position is going to be after, I don't know, let's do 6 seconds. All right? So after 6 seconds, our displacement is velocity times time. So we're going 3 meters per second for arbitrarily 6 seconds. There's no reason I chose 6. That gives us 18 meters. That's how far I went forward, right? So now I can figure out what my position is at the end of that time. Changing position is final minus initial. So let's see, I went 18 meters. I started at a position of 5. So my final position is 23. So what I just figured out is after 6 seconds, my position is 23. So I'm going to go over here. Position of time of 6, position of 23 is right here. And then I just connect the dots. Oops, I guess we'll do it in black. All right, so there we go. All right, now some of you are thinking, well, couldn't I just keep adding 3? And yes, you can do that, right? Because every second you're going to go 3 meters. Every second, 3 meters. Every second, 3 meters. But, you know, what if the time was like 400 seconds, right? Then it would be ridiculous, right? So the idea is I knew the velocity was constant, so I knew it was going to be a straight line. So I just found any other point on the line and connected the dots, okay? This is why I said the time was arbitrary. You know, I could have chosen 8 seconds, and then I would have gotten this point, and then connect the dots. All right? So this one's basically the same thing. Your starting position is 7 meters. After 6 seconds, the position is 19. So just, you know, go over here. Oh, I don't know why it's 6 seconds again. That's a weird coincidence. This graph is almost impossible to read. There you go. And then just connect the dots again. So I don't know why I made an issue out of making a new one of these. So here we go. All right, and you could obviously, now that you've got this, you could definitely find your slope. And therefore your velocity. All right, next video, acceleration. Oops.